right, find me that limit. Anybody agree with number 1?
Just the second step. Would you multiply by like 1/3 because of these on the bottom, or would it still be 2? Like that was my question I had.
Sure. So what we said was yesterday that when you take this and you separate it all out, we have the x over the sine of 3x. Okay, so to match one of the rules that we have, we got to have a 3x on the numerator. So we multiply each of these by 3, and then to compensate for it, we multiply by 3 3's down here, which is the 27. 3 times 3 times 3 is 27. So we didn't affect it at all. We wrote an equivalent expression, but it helps us to get to those limits as 1. We recognize that the 4 over the negative 2 is a constant, which can be pulled out. Limit of a constant times a function equals the constant times the limit of the function. And we carry it all the way out. Any questions? That's what we did yesterday.
Is that behind the Swivl now?
Yeah.
Okay, because
Yep.
I tried last night.
Yeah, the Megan and Evelise upload it during first hour the following day. Yeah. Okay. All right. Next one. Limit as x approaches 2 of this. This one's kind of tough to visualize. And if you plug in the 2, you get indeterminate form, which is 0 over 0. And so we can't go anywhere with that. So we have to try to figure out, is there a way that we can work with this? Well, if you're bad with your algebra, then you would try to do something like this. Okay, that's a no-go. Okay, it doesn't work. Or you might try something, oh, there's 3 up here and there's 1 here, so that means there's 2 there. Okay, that's just breaking every possible rule for the limits, or for your algebra. So we have to figure out what can we do. Is it factorable? Okay, is it factorable? Does x minus 2 go into x cubed minus 8? Okay, see a couple of head nods. What do you get from that? So the top, this numerator actually factors, okay? Numerator factors in x minus 2 times what? X squared plus 2x plus 4. Is that what you said? Okay. So where did that come from? Okay. So it's a difference of 2 cubes. Okay. So these are some of the rules that you should know from algebra. So difference of 2 squares, that's easy. A squared minus b squared is equal to a minus b times a plus b. Okay, so what's a cubed minus b cubed? That's the question that we're after. Okay, well, some people want to try all different things here, but what it is it's a minus b times a squared plus ab plus b squared. Okay. Now, you could take my word for it, but I've taught you not to do that. So you'd say, well, I need to prove it to myself, so I'm going to multiply it out. So as long as we've got this problem right here, let's prove it. If you multiply those 2 together, which is what I'm going to do right now, x minus 2 times x squared plus 2x plus 4. Okay. This is the reason why I hate FOIL. Okay. Because it's multiple distribution. Okay. FOIL is really multiplying each of these terms by each one of the terms here, but it's only good for 2 by 2. And 2 by 2s are just one small part of where we live. So what we're going to do is we're going to multiply the x times each one of these, and then we're going to multiply the -2 by each of these, and then we get 6 terms, because it's 2 times 3, 6 terms, and then we'll see what we get. So I'm going to distribute the x times each one of these. So I got x cubed plus 2x squared plus 4x. That's the x being multiplied by each of these 3 terms. Then we'll do it with the 2, and -2 that is. -2 distribute to each one of these. And we get minus 2x squared minus 4x minus 8. Okay. Now look at what you got. What happens? Boom, 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 boom. So this is the same exact thing as x cubed minus 8. Okay.
So the a minus b, a squared plus ab plus b squared. You just memorize that kind of, just something
Something that you should, yeah, I would. It's really not that bad.
yeah.
Take a look at. So, by the way, and if this is plus a cubed plus b cubed, then these are alternated. No. That one stays the same. And you can prove it by just multiplying it back together. Now, if you don't want to do that, then you learned synthetic division last year, right? Okay. So synthetic division, if you remember how to do that, you can take x cubed minus 8 and divide it by x minus 2. Okay. Doing the technique that you have for synthetic division. I don't like synthetic division because it's just a lot of tricks that you're walking through these steps that mean nothing. Okay. So I prefer to do it by long division in order to figure that out. Okay. So what do we got? Well, this turns out pretty good. So this cancels, which means that this is the limit as x approaches 2 of this function. And now going back to where we were at the beginning of our limit stuff, this is just a parabola. It's a continuous function. There's no problems. There's no holes or asymptotes, so I can just plug in the 2. And so I get 2 squared plus 2 times 2 plus 4, which is 3/4, which is, bless you, which is 12. Okay. I can't prepare you for, I can't do an example of every single possible limit. So my goal has been to show you strategies for how to go about the problems so that you can, when you're doing your homework, that's the place where you get to see a wide variety of them. Okay? There's no way you can become a master at something by watching somebody do it. You can be good at it, okay? But you'll never be really good. And of course, you'll never be great. You have to do the work yourself. You ever heard of the 10,000 hour rule? 10,000 hour rule is a theory that came about by studying what makes somebody really great, or somebody that can really, how can you become an expert at something, okay? And they've decided upon the number 10,000 as the number of hours that you actually have to put into doing something before you can be considered, before you have the possibility of being truly great at it. 10,000 hours. The average person works 2,000 hours in a year. Okay, if you work a regular 40-hour week. So that's 2,000, 5 years. 5 years full-time at something can put you in the range of being an expert. Okay? There's lots of different analogies I can make about people who are good and then people who are great, and it's the people who really put the time in they become that. I guess if you just want to be average, that's your choice. But I've seen what you've done so far. I've looked into your eyes this whole time, and I know that you are so much better than that. Okay, we are moving on to the next chapter. We'll look at part 2, page 68 tomorrow. So those problems we'll look at tomorrow if you have any questions on those. Or if there's anything else that has come up regarding that. But we're moving on to the next section today. So this section deals with what does it mean to really be continuous. Okay, we're going to look at the actual dirty details of it, and the other half of it has to do with one-sided limits, which we've already done before. We know how to do one-sided limits. So I actually taught that in when we first started learning. So here's a definition of continuity. Suppose we've got a function, call it f, and it's continuous. It is going to be continuous at x equals c if the following 3 conditions are met. So let's stop and think about what it is that we're looking at. If I have some random function, I'll call it f, and we're going to look at it at some value of c. Okay? So some value of c that we're looking at. And what I want to know is I can look at this graph and say, yes, this is a continuous function. I can draw it all the way from the left to the right without picking up my pencil. That's the layman's term for continuous. But the question is, what does it truly mean to be continuous at a point? Okay? How can I tell if it's continuous at a point? Okay? That's what we're looking at. What are the conditions that need to be met in order for this to happen? Okay? We're going to break it down to the dirty details. So I think the first thing that has to happen is that f of c has to exist. We're establishing the rules for what it really truly means to be continuous at a point. If f of c doesn't exist, then this thing has no chance of being continuous because there's a hole right there. Okay? So that's our first rule, that this has to happen. That's our criteria. Okay? Can you think of another one, a criteria that must happen if the function is going to be continuous at this x value? We've already established that this point must exist. Okay? And what I mean by existing is it could be anywhere. You know, it's got to exist. Okay? Amanda? The limit has to equal the functional value. We call it the functional value because it's the value of the function. Okay? So we're going to put those into 2 steps. We're going to take what she said and say, okay, the point must exist, but that just means it could be anywhere. Okay? The second thing is that the limit as x approaches c of that function must also exist. which means as you come in from the left and you come in from the right, they got to match up. Okay? So right now, if I pull this out, part 1 and part 2 of the criteria for definition of continuity, this satisfies it. Okay? But what she said was they have to be equal. That's the only way that this locks into place. And the third criteria is the limit as x approaches c of f of x must be equal to f of c. That is, the limit equals the functional value, which what that does is it places this dot right in the hole. And that means the function is continuous exactly at that point. Okay? Now, I'm going to draw a couple of pictures, and we're going to see which times we have criteria that is met and which times we don't. So let's draw a couple of pictures and discuss continuity. Yeah.
What does one side of these mean?
That's with the little plus
Oh,
and the
okay,
minus.
so that's not your question.
Mm-hmm.
Why do we say f of c must exist and the limit must exist? Why can't we just say the limit is equal to the functional value?
Great question. Because in some circles, let me answer it this way. We're establishing that, I can see what you're saying, why can't we just go directly at it? Why can't we just say that? And I guess we could, but the first two are just establishing that those values are there. Okay? So I think it's just breaking it down into just the smaller units that we got there. Okay? Question? No? Okay. I'm going to draw a couple of pictures, and we'll have different C values. And okay, so here's the first one. And here is another one. What I want you to do for each one of these is tell me what conditions are not met. That is, if the function is not continuous. So tell me if it's continuous. So for each one of these, we're going to answer the question, is the function continuous at x equals c? And then if it's not, tell me the reason why. And we're going to use the criteria up there. Okay, you got a general question?
No, I was just gonna
Okay.
say one.
All right, let's do the first one. Megan, you want to take the first one?
It doesn't exist,
Okay, what doesn't exist?
if C doesn't exist, it has C.
So you're saying number 1 is the problem?
Well, there's a whole, but it's up there, I don't know.
It's up there. Tim? Rule 3, okay? Maybe we should go through it one of these times. Look at the first one. Does f of c exist? Yeah. F of c is with this dot right here. Okay? F of c is the dot. So f of c exists. Okay? Second one, does the limit exist? No, just look at it. They come in from different places. They don't match. So that blows it up, which automatically makes 3 blow up.
So if 1 or 2 doesn't work, then 3 automatically can't work.
Correct. All right, number 2. Is this continuous at x equals c? No. Okay? You can tell because you can't draw the line, you can't draw the function without picking up your pencil at x equals c. General term. All right, which one causes the problem? 1. Does f of c exist? No. Is there a dot? Did I plot a point? Nope. Okay. Does the limit exist? Yes. Okay. Is this one continuous? Yes. All 3 match up. And what's the problem here? Both of them. The limit does not exist and the functional value does not exist. Okay.